we started the conversation about what? Sorry,
Ionic bonds.
Do you want a bit of frosting from the box?
No, let's get rid of it. Donut Hut.
Oh yeah, best place to get donuts.
Really?
Yeah.
That's what they said about Hertz donuts. I think those are trash.
Those are expensive.
Okay, the
Donut Hut and
the
Cheap
Oreo
Hand.
one's the only good one.
If that's the only good one, does that make them good?
Well, Krispy Kreme only good one.
They have
anything other than Lay's?
Yeah, they have chocolate frosting.
But they're good.
But Lay's are way better. No, Cookie Cream's way
Anyway.
better. Donut Hut's only.
Okay, so really we were talking about not ionic bonds, we were talking about covalent bonds, but we were talking about the bond energy for something like CH4. And we talked about how the total energy needed to break this whole molecule down is spread between all four bonds. And we said all four of those bonds we just took an average and we made the assumption that all four of those bonds have exactly the same amount of energy needed to break them. We're going to see today, when we open up our books here, that that's not the case. We made an assumption that the molecular environment that it's in doesn't play a part in how much energy each bond needs to break. So, just quickly here, let's open up our book, page 361. Okay, because we really do need to take one really important consideration is really just looking at how sensitive a particular bond is to its molecular environment. Waiting on you, Emily. Okay, if you look at the bottom there, it shows a CH4 molecule breaking one of the hydrogen bonds sequentially. Do you see a trend there at all? The bottom of 361. The amount of energy required to break each carbon-hydrogen bond. Do you see any kind of trend there?
It goes down for each one that's been broken.
It does?
No, sorry. I looked at the wrong numbers. You're right.
So although the carbon-hydrogen bond is broken in each case, the energy required to break them varies in a really non-systematic way. You would kind of expect either it to be the first one to be the hardest to break and it gets easier as you go on, or the first one to be the easiest to break and it gets harder as you go on. But you don't see that. You see a jump in energy required to break the second bond. So it says something about the molecular environment that it has. Now, flip the page. So instead of worrying so much about and trying to memorize all the environmental situations that one might need to think about with regards to each particular bond, we're going to assume that all bonds act exactly the same. And you're going to see how this approximation is actually one that doesn't significantly change our overall answer. Okay, because we're going to actually do enthalpy of a reaction two different ways. All right? Now, if you look down there, the next set, you can see you got HCBr3, HCCl3, HCF3, C2H6. What does that particular data table suggest? You need to look to answer this question.
The ones that have more electronegative elements have higher energy. The balance fluorine.
That is actually a pretty good thing that you notice there. However, you're not breaking the carbon fluorine or the carbon chlorine or the carbon bromine bond. You're actually breaking the carbon hydrogen bond. But what you're saying is those other elements in the molecule do have an effect on that carbon-hydrogen bond. You're right. They do. The molecular environment that it has does play a part. Right? However, it's going to be a lot more difficult to know every single molecular environment, how each carbon hydrogen, and each carbon chlorine, and each carbon bromine, and each carbon, you name it, every single one. So what they've done is they've given us an average. And if you look at the big table on the top, you can see the average bond energy required to break every carbon hydrogen bond, every hydrogen bond, every hydrogen fluorine bond, and so forth. Okay? We're making an approximation. We do that a lot in chemistry, don't we? Alright? So, there is a relationship that exists then between bond energy and bond length here. As the number of shared electrons increases, the bond length shortens. What do I mean when I say the number of shared electrons increases?
The difference in
More
charge.
what?
The
Okay.
difference in charge.
Okay. And, you know, I ask really broad questions. So, 2 shared electrons versus 4 shared electrons versus 6 shared electrons. What's the difference?
The 6 would be a lot shorter bond length.
Yes. It's saying as you go from a single to a double to a triple,
Oh.
bond length shortens. Okay. What's the relationship between bond length and bond energy, do you think? Just curious. Do you have any idea?
Maybe the higher the energy, the more tightly held they are, so it's a shorter bond. Maybe.
Higher the energy.
Sorry, lower the energy. Sorry.
Okay. It's just tough because we got to remember that stability means higher low energy. Low energy. But the more stable bonds require more energy to break them. Does that make sense? So, if we're thinking about this, if I have a triple bond, its bond length is going to be shorter, which means it's going to be, the two atoms being bonded are going to be closer together, and it's going to take more energy to break them. So, it should make sense. A triple bond is going to be more difficult to break than a double or even a single bond. Does that make sense? Okay? And it has to do with the fact that your bond length is shorter. So if we look up here at this table, let's look at, you got a carbon-carbon double bond and a carbon-carbon triple bond. Okay? Look at the numbers there, top right corner. You see them? Okay? 614 for the double-double bond and 839 for the carbon triple bond. Now, that does not mean that a carbon-carbon triple bond has more energy. It actually means the opposite. You understand what I mean when I say that? A carbon-carbon triple bond, are you listening? I think you do not look like you're listening. Are you really listening? You're being 100% before God honest? You just based off while you're listening?
Focusing.
Not focusing? Okay. Alright. I'm not saying I don't believe you, it's just really hard to know if you're listening. When I look at you sometimes and you look like you're deep in thought on something else. But maybe you're deep in thought on chemistry. Okay? Anyways, the fact that carbon-carbon triple bond has 839 per kilojoules per mole, that means how much energy you would need to break it. Okay? So the carbon-carbon held together with the triple bond would take that much energy to break it, making those carbon-carbon bonds have higher, more unstable amounts of energy. Okay? So the most stable bond is a carbon-carbon triple bond of any carbon-carbon bond. It all goes back to the idea that stability has to do with low energy. It has to do with strong bonds. Do you remember that day where I put that table and we talked about how a weak bond has high energy and a strong bond has low energy? But it takes a lot of energy to break a strong bond, it takes very little energy to break a weak bond. Okay. Alright. we can actually use bond energy to approximate how much energy is going to result when a chemical equation or chemical reaction happens. Okay, so we already have one way to do this. Do you remember one way to figure out the energy of a reaction? We've done it before in a different chapter.
Energy of products minus energy of reactants.
Yep. Enthalpy
Yeah.
of reaction, which is the product's enthalpy of formation minus the reactant's enthalpy of formation. Now we're going to do it a different way, and we're going to do it with bond energies. So here it is. You might tell me why this is a negative number, why that's negative.
It's losing energy.
Yes. When bonds form, energy is released, right? When bonds break, energy is absorbed. It requires energy to break bonds, gives off energy to form bonds. And the reason why, probably, does this in your head sometimes have a hard time to process the idea that forming bonds releases energy? Okay, for a long time that was hard for me to grasp, but you got to remember, why do things bond? To be stable. If they're stable, they have less energy. Well, where does that energy go? Leaves. Does that make sense? So forming bonds releases energy because when those bonds are formed, they form lower energy environments. Okay? Alright, so here's how this works. We got all these weird things up here. Looks like an En times D. This is just the sum of the moles times the amount of bonds that you have.
Sigma.
That's not sigma.
It's not. That's quite similar to sigma.
Sigma's this.
What am I thinking of?
I don't know.
What's
I can't remember the name of that guy. to be
What's the
honest.
name for, what's the one for summation?
That is a sign for summation,
Okay.
but I don't know
Yeah, I don't know
what
why
the
it's sigma.
Greek symbol's called.
Yeah, sigma's not right. You're right.
Okay. Probably best way to just go over this is to do a problem. Okay, let's do. Do you have a problem in your notes? You have that one. Do you have one before that? Okay. Well, let's stay on that same page, and I'm just going to give you this one, and I'll have you do the next one on your own here. Or maybe we should do the next one on our own too. This is a little bit more tricky than just doing products minus reactants for enthalpy.
Go back, find the.
Nope, you're going to use the table on 362 to do this. Okay, so let's find the change in H using bond energies. Okay, and our bond energy equation was bonds broken minus bonds formed. So really that's reactants minus products then, isn't it? How do I say that? What bonds do we break? Yeah, but are those the reactants or the products? Reactants. So technically this equation is reactants minus products, isn't it?
Yeah.
Everybody see that? Okay? So our first bond that needs to be broken is what? Okay? HH bond. Find how much energy is required to break an HH bond. Now be very careful. For example, if I have CH4, how many CH bonds do I have? 4. What if I have that? See what I'm saying? You gotta be careful with that. Or if I had something like, I know this is kind of ridiculous, but I just want to prove my point. That's probably not gonna happen. But you have to take into consideration you got one CH bond, one CL bond, one CF bond, and one CBr bond. Right? So if you have to do the Lewis structures on these, just to kind of visualize how many bonds of each thing there are, do it. Does that make sense?
What do you do if it's double bond?
You might have to do a Lewis structure
Would
when
you
you
do
determine that.
2 times?
No, there's a double bonds in here.
Oh, right, okay.
Okay? So, we know that we have one mole of it. And what is the bond energy for an HH? Right there at the top. 432. Just don't want to multiply there. Okay, then I got another mole, but I only have one fluorine-fluorine bond. What is it for fluorine-fluorine?
154. Seems like a low amount of energy to break that.
So you'd probably say a hydrogen molecule, gas molecule, is more stable than a fluorine gas molecule. Does that make sense with your process of thinking? Why am I saying that? Why do I say that? Why can I say that? Why can I say hydrogen's probably a more stable, hydrogen gas is probably more stable than fluorine gas?
But it takes more energy.
Yeah. Which means it has to be more stable, right? Interesting.
Is it because fluorine's more electronegative, so it's the ball's trying to steal the.
I don't know, because normally you, I think if you would look at most of these guys, like for example, the HF bond, the second one up here, if you look, 565, but the HCl is 424, and as you progress down, the one that has the greater electronegativity difference is the one that's held the strongest. That makes sense, right?
Yeah.
Well, technically there's no electronegativity difference here. It's just two things really strongly pulling. It's interesting to think about. I'm not 100% sure why this one is less stable than this. I can rationalize in my head why HF is more stable than HCl, because you've got a stronger electronegativity difference, and so they're being pulled tighter together. Smaller radius, all that stuff. Okay, that would make sense from our lattice energy too, even though that's technically not an ionic compound.
The diatomic iodine is the same way. It's really low. So that's the third column.
Really?
Yeah. Maybe it's diatomic
Huh.
electronegative.
Well, hydrogen is diatomic technically.
Yeah, but also low electronegativity.
That's true.
Well, and
Is there a BR? Yeah, that's a little higher.
And sulfur is 266.
Weird. There's not, well, yeah. That's a sulfur-sulfur single bond. There's not
Yeah,
many
yeah.
sulfur-sulfur single bonds.
I know.
Okay? Minus, then, now, each of the HFs have one HF bond, but I have two of them. And what is the HF, like 400 something?
565.
Yeah, it's probably already got an answer here. Why don't you find it for me?
Negative 544. So it's not really it's released 544 joules to surroundings.
Yep, so what does that tell you about which one's more stable, reactants and products?
Yes.
Can everybody process that line of thinking, that if the enthalpy of reaction is negative, that's telling you that your products have to be more stable than your reactants? Because energy is being released. If it were positive, it would have had to have brought energy in to form your products, and you would assume that your products would have been less stable than if they were in their reactant form.
But there's like 99% of the time to be more stable because that's what they're.
Yeah, most of the time. But you can forcibly make things react, even though naturally they probably wouldn't.
But aside from like really weird things happening, it wouldn't happen naturally. Aside from like humans doing it,
Yeah,
like a
probably.
volcano or something. it
Yeah,
wouldn't
probably.
happen. Okay.
Unless there was some specific environmental thing that caused, yeah.
The volcano.
Okay, so now I want you to do the same thing, but I want you to do it how we did it in chapter 6 when we were doing thermodynamics, and we were doing the enthalpy of reaction using the back of your book. So you're going to have to go to the back of your book to find the enthalpy values. You guys remember how you treat H2 and F2 in this case? You remember? When doing enthalpy of reaction, how you treat H2 and F2? You don't remember? Bummer.
recognize it if you say it. I don't remember what we talked about. We'll see if you can find it.
Figure out what I was asking.
Yeah.
You should have been able to come up with that, I feel like, without having to look it up.
Oh, okay, yes, then I know.
Find the each ethics. The first products minus reactants, not reactants minus products, like when we're doing bond breaking, bond energies.
It's very close.
Should be. Is it 42 or 46? I can't remember. Is that 42?
Yeah.
Now notice, they aren't exactly the same, but I wouldn't expect them to be the same. Why wouldn't I expect them to be exactly the same?
Count the bonds for hydrogen.
No. That's not why. Why would I not expect these to be the same? I expect them to be close, but I don't expect them to be the same. Why not? Has to do with what I said earlier today.
Copper.
Yeah. This may not be necessarily the correct energy for this particular bond because it's an average of a bunch of cases where you have hydrogen bonded with fluorine. Remember how we talked about how it's not necessarily the exact bond energy for every situation? Okay? But it's a good enough approximation that'll keep things close. Alright? Now, let's end on the last one, a little bit more difficult here.
There's something about
You know those vocabs already. Right? Lone pair, bonding pair, you know what those are, right? Okay, well, let's do this one together just because it's a little bit of work. I mean, I might ask you to help me find some numbers and whatnot, but I would just say, for sake of time and whatnot, let's go over this together. We're trying to, again, here find the enthalpy for the reactant, but we're going to do it with the bond energy. With stuff this big, I usually break it down into finding the bond energy of all the reactants and finding the bond energy of all the products. Okay, so I just write down, okay, what are my reactants here? Okay? So, first thing you gotta do here is identify how many bonds you're dealing with here. So when I'm talking about a CH4 molecule, now you gotta keep in mind that it's 1 mole of it, correct? How many CH4 bonds do I have to deal with here? 4. And what is the number for the CH4 or C4 bonds?
413 for each one.
Okay? Now I'm then looking at the next particular guy, my Cl2 here. Each Cl2 only has 1 bond, but since I have 2 moles of it, I need to multiply it by 2. What's the chlorine bond energy? 239. Same thing for my F2. It's only 1 F2 bond, but I got 2 of them. And that's what?
154.
Now I'm just going to check and add all those guys up. Because that's what the equation asks us to do. You should get 2,438. Okay, let's go to the products. Am I going too fast? Are you staying with me? Okay? Now be careful here. If you don't know what the shape of this and the Lewis structure of this looks like in your head, write it out. Now I can do it in my head, and I'm assuming most of you can do it in your head. Yeah? Okay, how many carbon-fluorine bonds do I have?
2.
How many carbon-chlorine bonds do I have?
2.
How many fluorine-chlorine bonds do I have? 0. Okay? Now, if I had a 2 here, or a 3 here, or a 4 here, we'd have to think a little bit more, right? So I have 2 of my carbon-fluorine bonds, which are what?
485.
485.
So, yeah.
And I have 2 of my carbon-chlorine bonds, which is
339.
if there was a coefficient of 2 here, what would it really be?
4 and 4.
4 and 4, and then if it were 3, it would be 6 and 6, and so forth. Okay, got 2 HFs here. 565. Now we got 2 HCl's as well. 4 something?
427.
Now, you could probably all set this up all at once. Maybe I tend to show more work than maybe I need to. I just process things better when I write it all out. That's just my personal preference. Take it out a little, add all those guys together. 3,632. Okay, now we gotta remember, is it products minus reactants or reactants minus products?
Reactions minus products.
Okay.
Negative 1,194.
What'd you say the answer was?
Negative 1,194.
Is that right?
Yeah.
Yeah. That's your answer. Okay, the last 2 vocab words. Bonding pairs, lone pairs, are something you should already know. that's your lone pair. You probably, you should remember me using those words quite a bit. And there's your bonding pair. Okay, there is a section on the localized electron model, but it's not overly important in the big scheme of things, so just a vocab words for you. Questions? Did you guys get that, Griffin brothers?